Hi, folks. So, today in this brief video, we'd like to understand what is the fundamental nature of software. All right. So, what I would like to argue, and this is, rather informal with respect to what your professor would say, but I really think the professor would not disagree too much either. So this is to give you an idea. So what really is software, right? What is the fundamental nature of software? The kind of software you are using to view this video, or any software, a computer game, a calculator, a word processor, whatever, any software. What is its fundamental nature? What is it really? So it is nothing else but automata. What is automata? Uh, it is the plural of the word automaton. So what is automaton really? So very loosely speaking, it is a machine, right? How exactly we'll look into it. So very loosely speaking, it's a machine. It comes from the background of mechanical machines, you know, things which have moving parts, which are defined by mechanics, sub branch of physics. So that is where it comes from, but we'll explore this further. So there's also another way to define software. Software, what is software really? Software is an algorithm realized. And what really is an algorithm? Algorithm is nothing else but a sequence of steps to do something. So this would bring forth the question then, that what is the difference between automata and algorithm? What is the difference? Well, my take on this is that it's semantics. Fundamentally, it's the same thing. Different ways of looking at uh, the same thing, basically, no difference. For all that I care, and I'd like to argue for it, it's in a sense they capture the fundamental nature of software. So let's try to explore this a bit further. So you might have seen dynamos in action, right? So as you would remember, what is a dynamo? It is a it is an arrangement of some mechanical items. Let's say I have this matchstick or something pressed put over here. Then I have another one over here. Then I have another one over here. Then I have another one over here, stacked, so on and so forth. Let's say all the way till here. And how are they defined? Let's say they are defined in a way that at any given point in time, if I choose to push forward this first element, if I push it forward, this will lean on this guy. This will fall, hit this. This will fall, it will hit this, the third one, so on and so forth. All of these will, as time passes, they will keep on collapsing onto each other. And how exactly does that turn out depends on the arrangement that you have in place. So let's think of Dynamo in another way. Let's say if we were looking at it from the top, let's say now each dot defines um, a, a stacked up element of the Dynamo. Let's say so you have placed it like this. Each dot is a let's draw it again. Each dot is actually a stack, and let's say a matchstick, if you were to imagine it this way. So let's say we define a dynamo this way. Let's say we have our arrangement defined this way. Let's say we have, it all depends on how we have arranged it. Number one, let's say, let's say this way, and let's say, so let's say this is how we have positioned our building blocks of the dynamo machine. This is the sequence of positions. Each dot, remember, represents a matchstick, and we're looking from it at the from the top, and all we can see is the top of the matchstick. All right. So what would the behavior of the dynamo depend on? It will depend on two things. Number one is this position of each element, each matchstick, and number two, which element or matchstick is pushed first, right? The sequence. Which matchstick is pushed first? First, of course, implies time. All right. So just to give you an example, if we were to start from here, we push this guy first, what will happen? Let's say this is T0 at the time at which we pushed this first matchstick, and what would happen? They would keep on falling on top of each other at a different point in time. This will fall, this will fall, this will fall. And when it reaches this point, it is designed in such a way, positioned in such a way that when this guy falls, let's say at T something, let's say T7, it would start parallelly proceeding this in this direction as well as in this direction, right? These will start falling, these will start falling, and after some time, this will start falling this way. After some time, this will start falling this way, and over here, the machine will stop. At least this line will stop. Similarly, after T7, this side would keep falling on top of each other, all the matchsticks, and by virtue of its positioning and timing, they will keep on falling till it ends over here. The last match over here also falls, and the machine stops because there is no other match that can be pushed. Likewise over here. So of course, if you can imagine, if we were to be doing this differently, let's say, not this way, but let's say if we were to be starting from here, let's say this is because, right? Remember over here, we said which matchstick would start, would be pushed first. Let's say if we start from here at T0, if we push this. So the sequence that will happen in which the matchsticks would fall, in which the dynamo effect would take place, will be different over here, right? Okay, so now what's the point of all of this? The point is that this dynamo positioning and the choice of which matchstick to push first, this is an automaton. It is automaton, or in plural, automata. And it is also an algorithm, right? Because remember, what is an algorithm? It is a sequence of steps, right? So this is nothing else but a sequence of steps. How exactly? Because the sequence of steps is defined by virtue of this positioning of each individual matchstick, and also at what time to start this machine. We start this machine by pushing a matchstick, and also which matchstick to push. All of these are steps, clearly defined steps. And those clearly defined sequence of steps, what are they called? It's an algorithm. So this is basically, I would argue that in this case, this dynamo is a mechanical machine, something that we can typically relate to. But here's the insight. What it entails by virtue of its positioning, not by virtue of its material values, not by virtue of the fact that each matchstick is made of a small piece of wood. That is not its essence. The essence over here, what makes it an automaton, is these aspects: the positioning, the layout, which matchstick to start first, and what will happen from that point onwards. All of this is the essence of this machine, of this automata, of and it is also defined as an algorithm, right? its initial state is not an algorithm. So there are some several differences. But for example, let me just briefly hint at them here. The initial state of this machine is not really an algorithm. An algorithm can have a prerequisite that I need the machine in this state, right? But algorithm in its sense is just a sequence of steps. And automata is the definition of a machine, which is in terms of its the details of how that machine is realized over here by matchsticks mechanically, and also by virtue of the other uh, aspects you need to think of to get that machine running, right? Which over here is the positioning layout itself, and also the time at which a certain matchstick is pushed to trigger the effect of the dynamo, right? All right, so let's say if we quickly move, let's say we bifurcate into two parts. Let's say over here we have the dynamo, something like we saw earlier. So what is this? It is a mechanical machine, right? It is mechanical, but it has an algorithm, which is a sequence of steps. Algorithm. And let's say over here you have a calculator that you are a calculator program, a software that you are using on your laptop to function as a calculator. So you might be thinking that these are two different things, right? This mechanical dynamo machine and this software calculator that's running on your uh, laptop over here. Let's say that this is you have a calculator running on your laptop screen, but it's not really any different. Because why is that? Because over here the branch of physics that we use to realize this is different, is electronics, not mechanics. And electronics, of course, is an order of magnitude faster in terms of physical uh, change capability with respect to time. And also, but that does not change its fundamental nature. Remember, that is the point. And then again, algorithm here, right? So whoever the guy who wrote this calculator program programmed it in a programming language, and that program is nothing else but an algorithm, a sequence of steps, right? In this case, it would be some code in languages like C or Java or assembly or whatever, etc., etc. But that does not change its nature. It remains an algorithm. Just like over here, the mechanical machine that we had, the dynamo, the branch of physics it used was mechanics. The branch of physics we use over here in a laptop calculator is electronics. Over here, the sequence of steps is an algorithm. Over here too, it remains the algorithm. So as you can tell over here that this aspect of a machine, the branch of physics, has implications with respect to the realization of a computer or a computer program, right? Of software. It's important to understand that this dimension is only with respect to realization. It does not change the fundamental nature of software. What really is that fundamental nature? That is the type of machine this is and the algorithm that is used. That algorithm is basically software. So this is the insight that I wanted to give today, that the fundamental nature of software, this is how we define it. And I wanted to give it in contrast with respect to a mechanical machine and with respect to an electronics machine, and also highlighting that the fundamental nature of software does not really change, not at all. I hope it was useful. Uh, and There are always, of course, details on what kind of machine a laptop is this running on, if you break it down further, but that is all realization, right? there is a CPU, there is lots of tons of other stuff, RAM and device controllers, so on and so forth. But what are they really? What is a CPU? What is a device controller? These are all electronics circuits at the end of the day, right? So it's a branch of physics used to realize the machine. It does not have any bearing on the fundamental nature of software. That is the point I want you to take away with yourself. All right, hope it was useful. Take care, folks. See you later with something else.